Objective 1.7, Quadratic Applications. So in this lesson, our objectives are to set up equations to represent real-life application problems, to determine how to use the equation to answer the question, and to solve application problems using quadratic equations. So when we are solving quadratic application problems, there are a few things that we need to keep in mind. First, we need to think about how to set up the equation that represents the information that you are given. And so a lot of times that means looking at your information and deciding which form of the quadratic function would best fit the information you're given. So if you're given something about a vertex, then vertex form would be a good choice. If you're given information about intercepts, then intercept form would be a good choice. That kind of thing. Then once you've set up the equation, you need to determine what to do with the equation. And that's going to be based on what the problem asks you for. Some problems are going to ask you for something that requires you to solve the equation that you've set up. Whereas other problems are going to ask you to find a maximum or minimum value. Well, that is like the vertex point on your graph. So you're not really going through the process of solving the equation. You need to go through the process of finding where the vertex would be so you can figure out what that maximum or minimum point would be. And then you would proceed to use your equation to find whatever type of answer the problem is asking for. So let's take a look at our first example. It says you have made a quilt that is 4 feet by 5 feet. You want to use the remaining 10 square feet of fabric to add a decorative border of uniform width. What should be the width what should the width of the border be? Alright, so first of all, we know that what we're missing, what we're trying to find, is the width of the border. So we're going to make that our variable. And then in problems like this that are geometric in nature, I highly recommend that you draw yourself a picture. It's a lot easier to sort out what you know and what you need to figure out if you draw a picture. So here's my quilt, and here's the border that's going around my quilt. And then I can label the information that I know. So I know that the quilt itself is 4 feet by 5 feet, and I know that the width of the border all the way around is whatever I'm going to find. So for right now, that's X. That also means then that I can label the entire length and width. So the entire width right here of my quilt with the border is going to be this 4 plus 2x expression, because I have the 4 from the quilt plus an x here and an x here. So the entire quilt, when it's all done, will have a width of 4 plus 2x. Similarly, I can figure out what the length will be, what that will represent, by looking at the 5 that I know from the quilt plus the 2 x's on either side to get this length. So even though I don't know exactly what the length is, I can come up with an expression to represent it, and that's very useful. So what I'm interested in is figuring out how to get the orange part to equal the 10 square feet. Okay, and so I've decided to take the area of the entire quilt and subtract the area of just the blue part, and that should leave me the area of this orange border part. Okay, so if that's what I'm trying to do, I need to use the expressions that will let me do that. Okay, so My first step will look something like this. I have the area of the total. Well, that's going to be length times width of this whole thing. And so that's the 4 plus 2x here times the 5 plus 2x here. That represents the area of the total thing. Then I want to subtract from that the area of the blue. So that's just this part, which was 4 by 5. And so the area of the blue is right there, 4 times 5. And then we know from the information that the border itself, which is the orange part, can only be the 10 square feet of fabric that's left. So now we actually have ourselves an equation that we can work with and try to solve for x. Since there was nothing in this problem that asked for any kind of maximum or minimum, we can assume that we need to solve for this. So I'm going to start by cleaning things up a little bit. I'm going to FOIL the 4 plus 2x times 5 plus 2x to get 20 plus 8x plus 10x plus 4x squared. And then I'll subtract from that 20 from the 4 times 5, and that's still all equal to 10. And so you can see that my 20s are going to cancel out here and here. I can combine my 8x with my 10x, and I can move the 10 over to the other side. And so I end up with 4x squared plus 18x minus 10 equal to 0. Now, in order to solve this, I can look for lots of different things. I can look for factoring. I can look for using square roots. I can look for completing the square. I can look for the quadratic formula. Whatever method that seems to fit the equation is fine when you're dealing with applications. Now in this case, I do notice that 4x squared, 18x, and 10 all seem to have a common factor of 2. So I am going to make my life a little easier by dividing that 2 out. So I'm looking now at 2x squared plus 9x minus 5. Now I noticed that I can actually factor this. So I chose to factor. You may choose a different method, and that's fine. It should not affect your answer. But I realized that 2x squared plus 9x minus 5 can be factored into 2x minus 1 times x plus 5. Which means when I go to solve this, I get x values of 1/2 and -5. Now, because we're dealing with a quadratic, the theoretical solutions have 2, a 1/2 and a -5. But if you now put that into the context of the problem, think again what x represented. X represents the width of my border. It doesn't make any sense to have a width that's -5. So even though -5 is theoretically a solution to the equation, it is not a solution to the problem because of the context of the problem, because of what x represents. So the only reasonable answer to this problem is x equals 1/2, or that the width of the border should be 1/2 foot wide. Alright, why don't you give one a try? Similar type of problem. Make sure you read the problem carefully, set up the equation that you think represents it, and then solve the equation to see if you can figure out your width of x. When you think you have it, come back and we'll check your answer. Alright, so let's check your answer now. So x has already been identified in the problem as the width, and so we know that we need to use that to set things up. So 12 plus 2x times 8 plus 2x represents the entire garden. I'm going to subtract from that the red roses, which is just the 12 times 8 part, and that should give me the border, which is supposed to be the same area as the red roses, so that's also going to be 12 times 8. So When I set up my equation, I notice that the 96's on the left side cancel, but then I also have the 96 on the right side that I need to bring over. 4x squared plus 40x minus 96, all of those terms can be divided by 4. So that makes my life much easier, where I only have to solve x squared plus 10x minus 24, which factors into x plus 12 and x minus 2. So the solutions I get from the equation are negative 12 and 2. But again, the only reasonable solution is the positive 2, because a negative x for width does not make any sense. All right. In our second example, we're looking at a very specific type of quadratic equation, but it's a very common type, and that is vertical motion. So there are two types of vertical motion problems and vertical motion models. One is if you are dropping an object, and one is if your object is launched or thrown. So if there's some kind of force behind the object when it leaves the hand, the gun, the cannon, whatever it is that's providing that force. So you'll notice here the biggest difference between these two models is the v sub 0 times t. In a dropped object, we do not have that term because we're assuming there is no additional force being given to the object. We're simply letting go and dropping it. With launched or thrown, we do have that term because we have that extra force behind the object. Everything else, though, is the same. Our h out in front is height, represented in feet, and that is sort of the ending height. Where does it end up? We also have our negative 16 t squared. That negative 16 is a constant value that comes from the gravitational constant. Then we have an h sub 0 as well. So we've got two different h's in these models, and that h sub 0 represents the initial height. So how high above the ground was the object when the whole situation started? And then when you do have this v sub 0 t term, the v sub 0 represents the initial velocity. Okay, so that's the measurement of that force behind it. And then the t simply represents the time since the object has been dropped or thrown, and the height represents what the height of the object is at that particular time. And time is measured in seconds. All right, so let's look at a problem where we might use this. It says a baton twirler tosses a baton into the air. The baton leaves the twirler's hand 6 feet above the ground and has an initial vertical velocity of 45 feet per second. The twirler catches the baton when it falls back to a height of 5 feet. For how long is the baton in the air? So the first thing you need to ask yourself in problems like this is the object being thrown or dropped? Now in this case, we can see that it's being thrown. It was thrown up into the air. Okay, tosses a baton. It's thrown up into the air. And so we know then that we need to use the model of h equals negative 16t squared plus v sub 0 t plus h sub 0. So then we need to start identifying those pieces that we can substitute into our model. So the h that we want right here, this is the h at the end of the problem. So where does the baton end up at the end of this time that we're trying to figure out? Well, that's this piece of information right here, the 5 feet. Okay, so our h here is going to be the 5. The t is what we don't know because we're being asked for how long is the baton in the air. So the t is going to remain our variable. The v sub 0 is the initial velocity, and we're told right here that initial velocity is 45 feet per second. And then finally we have our h sub 0, which is initial height. The initial height of the baton when it leaves the twirler's hand is 6 feet. So we need 6 for that term. So now if we substitute all of that into our model, we get the equation that 5 equals negative 16t squared plus 45t plus 6. So this now is what we need to solve. Again, there was no indication of max, min, how high the baton got, anything like that. It's just asking for how long. So we're going to solve for t. We're going to start by subtracting 5 from both sides. And then probably in this case use the quadratic formula. Now, with application problems, we do not need to leave our answers in exact form, especially when we're dealing with a quadratic formula and we can get some kind of funky answers because of the square root. If I were to go to someone who had this question and go to them with an answer of, oh, by the way, I figured that out, and your time would be 2 plus or minus the square root of 15 over 3, they would look at you like you just grew 4 heads. Okay, that doesn't make any sense to most people. So in application problems, you are allowed to work these out, possibly on a calculator, and actually get decimal, rounded, approximate answers. Okay, so when we put all of our A, B's, and C's into the quadratic formula, we can work this out and then actually plug it into the calculator. So we get a t that's approximately equal to negative 0.022 and a t that's approximately equal to 2.8. Now again, remember what t represents. It represents our time. So a negative time is again not going to make any sense as an answer in the problem. So the answer to our question is the baton would be in the air for approximately 2.8 seconds. Now, what if the question actually had asked you what is the maximum height the baton would reach? That's not a solve the equation problem anymore. Now we would be looking for the vertex of the parabola representing the height of the baton over time. So we take that same equation that we set up, but this time without the h value, because we're not interested in the height at a particular time when she catches it. We're interested in leaving this h as an unknown, and we're going to find out what is the highest height the baton reaches. Okay? So now we take this equation and we go through the process of figuring out the vertex. So I would recommend using the negative b over 2a to find t. That's going to be a negative 45 over 2 times negative 16, which comes out to about a 1.4. So if I put 1.4, that is still t. So that's the time at which we hit the maximum height. We need to now put that into the equation for t to find the actual height. So if we work that out, we end up with about 32.64. That's now the height, so that's the feet. And so we can finally answer this question by saying the baton would reach a maximum height of about 33 feet, just a little less than 33 feet. Okay, so that's what I mean by the difference in problems. This is the type of problem that's asking you to find the vertex, not the solution. All right, why don't you give one a try? Read the problem carefully again, set up your equation, do what you need to do to answer the question, and then when you're ready, come back and check your answer. All right, so based on the information we're given, we're told that the basketball teammate catches the basketball at 11 feet above the court, so that's where we want things to end up. We are told that we have an initial velocity of 21 feet per second, so that's our v sub 0. And we're told that the player releases the ball 5 feet above the court, which is our h sub 0. So if we subtract the 11 over to get our 0 on one side, then we can set up a quadratic formula. And notice this time we get two answers, both of them positive. Now, how is that possible? Well, it actually makes a difference whether the teammate catches the ball on the way up or on the way down. So the ball is traveling up and then starts coming back down. Okay? And somewhere right here is the height of 11 feet. So when they tell us that the teammate catches the ball at 11 feet above the court, they don't tell us whether he's catching it here when it's on its way up or here when it's on its way down. Both are possibilities. Both of these are positive answers that make complete sense, and so it just depends. And since we aren't told which one happens, probably you need to include both as your answer. So the ball is in the air 0.42 seconds if it's caught on the way up, or it would be about 0.89 seconds if he catches it on the way down. All right, one more type of problem. In this example, we're told that the woodland jumping mouse can hop surprisingly long distances given its small size. Write the quadratic model for a mouse that can jump 6 feet from its starting point and can get 3 feet high. Now this may seem like a vertical motion model, but it's not, and there's a couple of clues that let you know that that's the case. The first clue is that there's no indication of time passing here. The second clue is that there is no initial velocity. There's no v sub 0. We're not told with what force the mouse jumps. So in this case, we're not looking at just plotting height with respect to time. We're actually looking at what is the equation, the quadratic model, for the actual path that the mouse takes. Okay? So that means our x-axis is actually going to represent horizontal distance, not time. Our y-axis still represents vertical distance, but that x being horizontal distance is very different from time, and therefore that's what makes this not a vertical motion model. So, if we are being asked to write the quadratic model, we need to come up with what the equation is based on what we know. And in this case, based on the information, there's actual two possible approaches we could use. One approach would be to use the vertex form. Since we are told that the mouse reaches a maximum height of 3 feet, since it's the maximum, we assume that that happens at the vertex and therefore would happen midway in his jump. So that technically means the vertex is 3, 3. And we can put that in for h and k. Now, in order to figure out the a in front of our quantity squared, we need another point that we can put in for x and y. And that other point in this case is the fact that the mouse will be back on the ground 6 feet from where he started. So that means we can use the point 6, 0, put 6 in for x, 0 in for y, and now we can solve for a. So we subtract the 3 from both sides first. We can also take the 6 minus 3 and square it, but make sure you keep that with a since it's being multiplied. Then we divide both sides by 9, and we get an a value of -1/3. So with a, h, and k in place, we get an equation of y equals negative 1/3 times the quantity x minus 3 squared plus 3. And that is one possible equation to represent the path of the mouse. Now we could have also done this using the intercept form, because we know that the mouse starts at 0, 0 and ends at 6, 0. So we can use 0 and 6 as our x-intercepts, P and Q. Now again, in order to figure out A, we would need some other point to substitute x and y. And again, we're going to go back to the idea that 3 feet high would have to happen halfway in between, and so we have this point of 3, 3. So we put that in for x and y, and then we solve. And you'll notice we get the same exact A. That should not be a surprise to you. So it doesn't matter which form you use, you should get the same A either way. But when you substitute it back in, the form of the equation is a little different. We now have the equation y equals negative 1/3 times x minus 6. It represents the same parabola. It is just written in a different form. And so this is another possibility for the path of our mouse. Now, what if in this case we were additionally asked how high the mouse would get when he was 2 feet away from his jumping spot? Well, 2 feet away would be the horizontal distance, and that would be the x value. So using either of these equations, we can now substitute 2 in for x and solve it out. And we end up with y equal to 2 2/3 either way. So when the mouse is 2 feet away, he would be 2 2/3 feet above the ground. All right, one more practice for you. Go ahead and give this a try based on the information you're given, based on what you see in the picture, and based on the fact that you want to actually write a quadratic model first and then use it to answer the question. Pause the video while you try this out and come back when you're ready to check your answer. Alright, so in this case we don't really have any information about the vertex. In fact, that's what we're being asked about. How high is the road at its highest point? That would be the vertex. So based on what we have, our only real option is to use the intercept form, because we know the road is here at 0, 0, and then the other end of the road is here at 24, 0. So if we use 0 and 24 as our intercepts, then we can use this other point that's being labeled here as 17.2, put that in for x and y, and we can solve for a. So a ends up being about negative 0.0017. Once we establish that, we can put that back into our equation, and this right here answers the first part of our problem, which was to write the quadratic model for the surface of the road. So that is this part right here. Then we can use that equation to figure out how high is the road at its highest point. So again, that would be the vertex. The vertex would happen halfway in between here. So if this total distance is 24, then halfway would be 12, and we can put 12 in for x. And that ends up giving us 0.2448. So we end up with an answer that the road is about 0.24 feet high at its highest point. Alright, so that should give you some good information and some good examples that you can refer to as you work on the practice problems for Objective 1.7 in your booklet. If you need help, make sure you find the resources that will help you answer any questions you have, your textbook, Mr. Frere King, writing me an email, whatever works. And don't forget to check your completed practice with the answers posted on Canvas so that you know if you're on the right track. All right, that's it for this lesson. We'll see you next time.